Well, hello and good afternoon or good morning, and thank you very much for joining us for the Optics.org hosted webinar by Laser Quantum. The webinar today will be on free cycle optical parametric amplifiers, the next generation of high power amplifier systems. Presenting the webinar will be Thomas Vinhammer. Now, this webinar looks into the pioneering field of free cycle OPCPA systems, an important and enabling technology for applications requiring high photon flux. The webinar will cover the technology and physics of modern OPCPA systems, the scalability in terms of pulse energy and repetition rate, and focus on a few cycle pulse generation with stable carrier envelope phase. Thomas himself graduated from the University of Stuttgart, Germany, with a diploma in physics and went on to complete his doctorate at the Max Planck Institute of Nuclear Physics on Heidelberg, Germany, on the production of the use of ultra-short laser pulses. Thomas furthered his research at the University of Hanover Institute of Quantum Optics as a research associate coordinating projects in the field of ultra-short pulse lasers. In his professional practice, Thomas was head of development at Nano Layers Optical Coatings, GmbH, working with ultra-short pulse lasers. In 2008, he became managing director of Ventian Laser Technology GmbH, now Laser Quantum, and has continued to develop commercial firsts in ultra-short pulse lasers. Thomas authored 27 peer-reviewed scientific papers with more than 350 citations, and his H index is 13. Thomas, I pass over to you.
So, thank you very much, Rob, for the kind introduction. I would like to welcome you also on behalf of Laser Quantum to this webinar about few cycle optical parametric amplifiers, the next generation of high power amplifier systems. And in the next 45 minutes, I hope to give you an overview about this fast developing technology and show its potential. OPCPAs are not only an exciting field of physics by itself, but also an enabling technology for a large and growing number of rapidly developing applications. I will focus mainly during my talk on high repetition rate, few cycle passes, where the OPCPA concept has significant advantages over other amplifier technologies, and it will not be possible in the scope of such a webinar to cover this whole wide field. So this will be the main focus. In the beginning, I want to give you a short motivation on why this is an interesting topic and such an important enabling technology. And I just listed selected applications where few cycle and high intensity laser passes are very important as a light source. Most prominently, high harmonic generation and attosecond physics should be mentioned here. The high laser intensity is used to drive the electron, in this case far from the parent ion, accelerated, and upon recombination, coherent radiation can be emitted, and this gives yield to attosecond pulse train and discrete harmonic spectrums. If you use a longer pulse duration driving laser, for few cycle pulses with stable electric fields, so-called carrier envelope phase stabilized pulses, also allow the generation of isolated attosecond pulses. And this enables extremely short probing times in the attosecond regime, which allows you to study electronic processes within atoms or small molecules, or even electron emission time delays from surfaces. So this whole field of time-resolved XUV spectroscopy is fast growing and gives insight into interatomic or molecular processes. And as the XUV conversion efficiency is in the order of 10 to the minus 4 or even lower, a high IR photon flux is often needed for the driving light source. Second example is called light-matter interaction in general. This is often studied in so-called cold trims or reaction microscopes, so this is the sketchy image here. And they allow the full reconstruction of momentum and thus enables a deeper understanding about the ionization process itself and also from atoms or from molecules. This is only really possible if the particle density is low, so in these cases often high repetition rate is beneficial to gain significant statistics. As another example, bioimaging can be mentioned here, which normally profits from several operation modes, so wide tunability or fast switching between wavelengths to identify functional organs within the cells. are quite useful. Also 2 or 3 photon microscopy is often used, especially for deep tissue imaging. Radiation in the mid-IR is quite helpful, and the BRAIN initiative in the US is, for example, has as a topic deep tissue imaging of large volumes, so quite significant power is also needed in this regime. Another example called attosecond nanophysics here. I summarized the objective to combine nanometer resolution, for example, from a near-field microscope, together with femtosecond resolution in the time domain. And in many groups, mid-IR or terahertz radiation is used here directly to probe the molecular vibrational bands, a wavelength range that's quite difficult to access with other laser technologies. And also, a lot of efforts are going on in research groups worldwide to do actually electron microscopy, so the ultra-short intense laser pulses here used to drive electrons from a tip within a short time scale, so femtosecond resolution from the electron bunch is used to time-resolved structure analysis. Similar objective is done in ultra-fast diffraction imaging. So here, time-resolved X-ray diffraction is used to analyze the structure often of large biomolecules, and those kind of experiments are often performed at synchronous-type facilities, or the FEL, like in Hamburg. So these are not tabletop experiments, and there's hope that with the growing OPCPA development, they can be replaced by tabletop systems in many cases. Of course, there's always a general interest in XUV radiation for lithography, and as shorter wavelengths allow structuring of smaller sizes, there is also, if it would be possible, to develop a compact laser source which emits radiation in the nanometer range. This could have a follow-up to industrial applications on a wide scope. So, as you have seen from these examples, already we can identify a dream light source that would provide a combination of parameters, as you've seen here in this summary. So, few cycle pulse duration, high repetition rate, CEP stability, low noise, tunable from UV to mid-IR, high peak power and versatility, and least but not, and also as a last point, user-friendliness is then for the application a quite important point. So the current workhorse of ultra-fast applications is still without doubt Tizapha-based laser systems and amplifier. So they are well established for over 20 years and triggered a revolution, opening up quite a new manifold of new applications. And especially when these systems were offered commercially, making them accessible to a wide range of users. But comparing the list above, however, you can see that Tizapha-based systems are often located in the quite long pulse duration, above 25 to 30 femtoseconds, and low repetition rate regime, so they are not really able to fulfill all these requirements, especially for high photon flux. So this is one of the driving factors why OPCPA technology has experienced such a boost, because with the increased demand from applications, there is quite an interest to develop new light sources apart from these Tizapha-based systems. So OPCPA is a quite old concept, but lately, mainly due to the availability of high-power pump lasers, it has experienced a dramatically fast development. Okay, so here's an outline of my talk, what I want to present you in the next 45 minutes. First of all, I want to summarize more or less the benefits of OPCPA technology and give you a short overview about work that has been done in this field lately. In the second part, I will focus on the OPCPA systems as they are done with laser quantum, which are mostly CP stable and few cycle pulses with high repetition rate. And in the end, I will go a bit into the physics of the OPCPA or parametric amplification itself and show you some simulations and experimental results that we've done here. So I will start now with, first of all, going a bit more into detail how an OPCPA actually works. In principle, the scheme is to transfer the strong pump path, transfer the energy to the broadband signal path, and this is done by a nonlinear crystal, which more or less provides the nonlinearity for this process. And the difference between pump and signal energy is then carried away by the emission of an idler photon. So the crystal in this case is parametric, as it only provides a nonlinearity but doesn't absorb any light directly. So in this process, of course, energy and momentum conservation has to be fulfilled. As I already mentioned, the energy difference in photons between the signal and the pump is carried away by the idler photon, as you can see in this simple example. And the momentum conservation has to be fulfilled, which is in case of light, can be translated in a k-vector relation. And this relates in the end to a phase matching condition that we have to fulfill to do an efficient parametric amplification. Here you can see that this is kind of the hardest restriction for band in terms of bandwidth, but it can be overcome, as we will see in the further slides, by choosing a non-collinear geometry, because you can always find some phase matching for the k-vectors if we go to this non-collinear geometry. So this is the basic principle. I want to start now with a comparison of amplifier systems, how they are built, and what is actually the advantages and disadvantages between the comparison of Tie-Sapphire-based amplifiers and OPCPAs. So a traditional multipass amplifier based on Tie-Sapphire, starting with an oscillator, then the passes are stretched and are amplified in a multipass or regenerative setup, and then compressed in the end to the final output parameters. As you typically amplify from nanojoules to a millijoule level, even though, as you can see here, the emission bandwidth and gain bandwidth of Tie-Sapphire is very wideband, it's still, with this high gain factor, you can experience quite dramatic gain narrowing. So no matter what you start as a seed oscillator, you will typically end up with 25 to 30 femtoseconds at the output of this amplifier. So you can do some tricks to reach 20 femtoseconds. But in the end, if you want to reach the few cycle regime, you normally need a nonlinear compression using hollow core fibers, which makes the system more complicated and less energetic. One of the other main drawbacks of the technology is that you essentially have a quantum defect between the green pump photons at 532, for example, and the 800 nanometer photons that are amplified. And this quantum defect is, in this case, deposited within the Tie-Sapphire crystal as heat. So you have to do extensive cooling if you want to scale this up to higher average powers. And this is quite a limitation, especially if you want to go to high repetition rates. So at low kilohertz repetition rates, this limitation also comes from the Q-switch pump lasers that are often used in this case, which have nanosecond pulse duration and are often operated below 10 kilohertz. And this is connected also to this heat problem. In comparison, OPCPA systems normally start off with a broadband Tie-Sapphire oscillator or fiber oscillator plus white light generation. And you have a main amplifier, which is in the work that I present here mostly based on ytterbium, which is quite efficient. And then you convert it to the green or use a fundamental. And the aim is to transfer this energy to your signal path. And this can be done, as you can see here, in one or two stages. And one of the advantages is that because of the high gain, this can be done in single pass. So you can build it in general quite compact. And you can achieve a quite broad gain bandwidth, as we will see later. So you don't suffer from gain narrowing in most cases. Another advantage is the scaling potential that you have, because the quantum defect, let's say, between pump photon and signal photon is carried away here optically by the idler. So it's not stored within the crystal, but emitted as radiation, which can actually be used for further applications. So you can, in general, apply quite high pump powers to the scheme. And one of the main benefits, and one of the, in my opinion, one of the main driving factors is that we have a very much scalable ytterbium-based pump laser here with a few hundred femtosecond pulse duration. And in the next slides, I will just show you a few examples of the power scaling that has happened in the last few years in this regime. So, in principle, there are three main technologies that I want to mention. First of all, there's fiber amplifier technology. So you start here with an oscillator, as you can see in the graphics below. You stretch it, you pre-amplify it in all fiber-based setup. Then you have a main amplifier and a compressor. And ytterbium is a quite interesting material for power scaling here because the quantum defect between pump wavelengths around 976 and the 1030 emission is quite low. The pump diodes are commercially available for a good price ratio, and ytterbium is a quite efficient material. One of the main aspects in all the three concepts I will be presenting is cooling properties, and in these kind of rod-type fibers, you cool from all directions more or less along the fiber, so you have quite good heat extraction from this fiber. You can see here a small list of results that have been achieved. So there's almost 1 kilowatt at full repetition rate, high peak power in the gigawatt range, and even in this technology, which is normally more limited by nonlinearities, millijoule level pulses have been achieved, and you can see here more details in these publications. So another technology for high peak power, high average power or high energy is a so-called slab amplifier design. Here the crystal has a high aspect ratio, so that it can be cooled from top and bottom quite efficiently. And as you can see in this amplifier design, as the seed goes through the amplifier crystal, it increases in size to manage the nonlinearities. And this is also a commercial product here, as you can see. Scientifically, high rep rates on the kilowatt range have been achieved with 600 femtosecond pulse duration, so they are quite ideally suited also to pump an OPCPA. And you can also, because the nonlinearity is significantly lower, operate this at quite low repetition rates and reach high energy here, in this case 160 millijoules. And again, I refer for more details to this publication below. The last concept I want to mention, also based on ytterbium, in this case ytterbium YAG, is a so-called thin disk regenerative amplifier. So here the thin disk concept allows a two-dimensional cooling of a very thin laser material from the backside, so it also is quite efficient to extract the heat. You can see here on this schematic drawing that you also start from a sapphire or fiber oscillator, you stretch it, and then you go into a regenerative amplifier, in this case applying one thin disk. So you go through the pocket cells, you couple out and then compress it. And in this example, 170 watts at 6 kilohertz have been extracted from this, and an OPCPA has been pumped at actually 6 kilohertz, so sapphire repetition rate more or less with 1.8 millijoules and directly sub-7 femtoseconds. If you just concentrate on the region, you can also use more than one thin disk module, and here also kilowatt powers at 5 kilohertz, 200 millijoules are state-of-the-art in the meantime. And also this is commercially available, and for more details again, please check the references here. Okay, so you can see there's a lot of power scaling going on, but apart from power scaling, also the accessible spectral bandwidth is quite important. Here on this slide, you can see a summary of laser active material based on inversion. So it's sapphire is the most prominent example here. There are other materials that allow lasing oscillators and amplifiers at other wavelength ranges, but often they lack the high power pump lasers needed to meet the absorption band, and crystal quality heat extraction is often a problem in the system. So apart from sapphire and other prominent examples, it gets often quite difficult to operate these lasers at wavelengths out of the visible range, mid-IR or UV. So here, that's also an interesting aspect for OPCPAs. As we have been discussing phase matching, this is an example for a standard BBO pumped at 520 nanometers, and you can see from this phase matching diagram that we get a magic angle, so-called magic angle at 2.5 internal angle, where we can amplify a whole bandwidth from 650 to 1100 nanometers in this case. There's also an associated idler, as you can see on the left side of this diagram, in the dotted lines here. And depending on geometries, and we will come back to this in the end of my talk, there's also parasitic second harmonic generation that can occur. Below the graph, you can see the K-vector diagram. You can see that the idler essentially takes a phase mismatch to fulfill the phase matching conditions. What is interesting about this concept, more or less, is that the same diagram you can also draw at a different pump wavelength. So this now is pumped in the blue, and you can see that we can also achieve a broad bandwidth, but now in the range of 450 to 700 nanometers. So you can already see from this diagram that different wavelength ranges are quite easily accessible by choosing a different pump wavelength. So this is now the tripled pump from ytterbium at 343 nanometers, and choosing the right geometries or crystal. So on the next slide, you can see just for BBO possible wavelength ranges taken here from the publication from Christian Manzoni, summarizing the bands that are accessible already just focusing on this parametric crystal. That's not the end of it, actually. You can use other crystals, so LBO, especially periodically poled crystals, KTA, other crystals around there can cover different wavelength ranges, especially if you want to go to the mid-IR. And as all these pulses are highly intense and synchronized to each other, also frequency mixing is a quite efficient way to access different frequency ranges. So there's some frequency generation, second harmonic, difference frequency generation. All of these options are possible to broaden the spectral ranges. And on the next few slides, I will just show you some examples from literature what has been done, especially here in this publication here from the group of Jens Biegert at ICFO. You can see that you can do extensive frequency mixing. They start off from a terbium fiber laser, which emits two wavelengths, more or less, 1030 and 1550. And you start with a different frequency generation to make actually CP-stable CEDA. You stretch it, and then you synchronize a main amplifier to that provides, in principle, the energy for the process. And with all these mixing processes and specially designed piplins, they managed to have actually 5 outputs out of this OPCPA 860 kilohertz. And you can see that you can cover quite a wide bandwidth. In the later publication, they also managed actually to widen this and use the idler and produce radiation at 7 micrometers, so which is especially interesting for mid-IR spectroscopy. And you can see that you can achieve quite significant power here. Okay, one other target that many groups have is approaching the single cycle pulse. So these extremely short pulses, in this case a transform limit of 3.3 femtoseconds, can also be achieved by using OPCPA technology. In this case, you want to combine and synthesize the different wavelengths generated with an optical parametric amplifier, in this case from the group of Franz Kärntner. You can see they start off with an octave spanning telsophyte laser. They use the difference frequency and also the more or less fundamental, and with a balanced cross correlator, in the end they synthesize this to a sub-cycle waveform. And one of the main difficulties here is to have a good stabilization and carrier envelope phase control, so that you have a clean sub-cycle waveform without jitter. In another publication, they actually scaled this up even further. I don't want to go into details here. You can see the publications here. But in principle, you can use the main power to amplify here. In this case, you generate white light for having a broad band, and you use different channels to amplify those bands in parametric amplification stages. And in this approach, chirp mirrors are used for each spectral band to recompress them, and in the end, again, through a balanced cross-correlator and precise control of the relevant fields, you can try to synthesize these wide band to reach actually a transform limit of 1.9 femtoseconds and a 2-octave wide spectrum with quite significant energy. Okay, so this pulse synthesis that I have showed you is more or less a parallel approach. So you split up your seed in several channels. You use different colors and different parametric crystals to amplify them, and in the end you put all the spectral bands together. And the complexity is also to control these on a sub-cycle scale. Another approach would be to have a serial approach, so you can do a parametric stage, let's say pump with the green, then do white light and amplify then in the second stage the excess band that you have generated with the white light generation. In this case, you don't have to worry so much about the jitter, but the complexity, as we will see, is then in the compression, because you have all the bandwidth in one beam, more or less. Just very briefly to wrap up this topic, I want to show you the results that have been achieved in Hanover with this kind of concept. So you can see in black the initial seed oscillator, then in blue after the first NOPA stage you can see the amplified spectrum, so it covers more or less the whole bandwidth. The white light generated you can see then in green, and for the final stage pumped with the blue, you can see that you can nicely also amplify this short wavelength range and cover with the red over octave spanning spectrum. And in principle, this bandwidth would give you also 2.5 femtoseconds, so 1.2 cycle pulse at 650 nanometers. But then the challenge is to compress this, because with chirp mirrors this is a very challenging task. Okay, so a final topic that I want to address is CP stability of OPCPA systems in this short overview. So if you start with a white light seeded OPCPA, the pump laser in general, starting from a fiber oscillator and amplifier, is not CP stable. If you do second harmonic generation and white light generation for the broadband seed, both all beams involved will not have a CP stability. If you implement different frequency generation, so you go essentially to the mid-IR, you can have a CP stable signal. The idler in this case will not be CP stable. And if you pump the OPCPA with the fundamental and use the white light from the same source, the idler, which is more or less takes the difference phase between signal and pump, will be CP stable. So this is a concept that is often also followed. It looks different a bit if you go to a Tizafire-based OPCPA system. In this case, as you will see in the next slides, we will start from an octave spanning Tizafire oscillator, which can be quite easily CP stabilized. We go through a fiber-based pump laser, and the broadband signal will maintain more or less the phase stability within the amplification process. Also, in principle, the pump laser should maintain CP stability, and the idler then, as a result, will also be CP stable. There's some work about coupling from pump intensity to phase noise, and in general, you normally apply a second feedback loop to control the phase jitters that you might have in the amplifiers. But yeah, this is manageable. Okay, so I will now go to the second part of my talk, which is focusing on the CP stable few cycle OPCPA systems that we built at Laser Quantum. Just to remind you of the applications that we were initially motivated us to go in this direction. They profit widely from an off-the-shelf, more or less commercial available system, as in the meantime these applications are so deep into details already and needs experts, so that it's very difficult if you're kind of spending your time with building the system yourself in the lab and maintaining them. So a commercial source can widely help you in focusing on your experiments. So the concept that we are following at Laser Quantum is starting from a broadband pulsar oscillator, which can be easily CP stabilized. We use the broadband output from 650 to 1 micron as a signal, and what is special about our system is that we have enough seed energy at 1030 nanometers to directly seed the fiber amplifiers. We don't need any nonlinearity for generating of the seed, and that of course helps you to have an intrinsically low noise and less low jitter system. We use quite short pump passes, as you will see, to go through 2 amplification stages, so that allows us to build quite efficient chirp mirror compressor in the end to go down to sub 8 femtosecond pulses as the output of the OPCPA. Here you can see a small picture on the bottom. Okay, so a bit more detail. This is a typical spectrum from the Vention dual broadband seed oscillator. So we can use here the bands in orange to do the direct CP detection. So what you do is essentially you take the infrared part, frequency double it, and do a direct interference to measure the carrier envelope phase beat and stabilize this. We can furthermore extract broad bandwidth, as you can see on the right, directly from the oscillator to seed our fiber amplifier. And then, so as we need no external broadening, neither for CP nor for the fiber seeding, this is an ideal front end for OPCPA applications in our opinion. Here's a schematic setup of the system. So as I told you, we start from this oscillator, then we go through a all fiber-based preamplifier, which includes the stretcher, pulse picker, and monitor ports. Then we have a fiber-based main amplifier and can do efficient second harmonic generation with these short pulses. So we have about sub 300 femtosecond pump pulses for ANOPA. As we can maintain quite short pulse durations for the signal pulse, you can easily compress it with chirp mirrors, which makes it quite efficient and stable. Here you can see a picture or rendering of the complete setup, which is in the meantime quite compact actually. So look further into details. You can see here the preamplifier unit and the main amplifier. There's also space for additional amplification stages, more or less, because in many applications it's important that you have synchronized output at different wavelengths, so it's also possible to have a high power output in the infrared or at the second harmonic. And then the NOPA stage has more or less, as you can see here, 2 NOPA stages, and we have an active delay control to avoid driftings between the 2 sides, 2 pulses, sorry. And you can also additionally access the oscillator output itself. So now I just want to present you some results that we did with these systems. In the left top corner, you can see more or less the bandwidth, which is one of the main benefits of this amplification technology for us, apart from the power scalability. You can see we enter the system here with a pulsar seed in red on this logarithmic scale. Then you see after the first NOPA stage, we can amplify the full bandwidth, and then also we can maintain this bandwidth in the second amplification stage. And this leads on the right side, as you can see, to quite short pulses. Here the transform limit is about 5.9 femtoseconds, and we measure a quite clean profile below 7, here 6.7 femtoseconds as measured with SPIDER. The output parameters that we have with the system is about 16 microjoule pulse duration, sub 7 femtoseconds, and at a repetition rate of 200 kilohertz. So it gives you a gigawatt level peak power and quite low noise. With the active delay stabilization, we can also maintain the stability within less than 1% noise. What is quite important also is that you can operate the system on a day-to-day basis. For that, we also have automated pointing stabilizations that kind of correct for temperature drifts or whatever you might experience in your lab, and that you have quite good beam profile. We will also address this part, if I still have time, in the end of the talk. It's not that is kind of a focus that you have to rely on in developing these systems, because the parametric process itself is quite complicated and you should not overdrive it, as I will address in the end of my talk. Yeah. So one of the benefits of OPCPA is also that high repetition rates can be easily achievable, and they can also be changed by just changing the pulse picker ratios and operating of the fiber amplifier. So this technology using fibers is especially good for high peak powers. And you can see here two examples that we can achieve. Here on the top left, you can see the second harmonic generated from the fiber amplifier in red at 200 kilohertz. And if we adjust the focusing in blue and 2 megahertz with the same efficiency, more or less, if we operate the same second harmonic without adapting the focus from 2 to 4 megahertz, you can see that it still works quite nicely, but with lower efficiency. The same is true for the parametric amplifier. So if we now use the second harmonic and operate the system at 200 kilohertz or 2 megahertz, we can almost achieve the same slope of the parametric conversion. So it's quite easy to extract more than 3 watts out of these systems. If we change to 4 megahertz without adapting any focusing in the NOPA, of course the efficiency drops even more, but you can still see that you can achieve more than 2 watts from the system without touching any optics, which is kind of the most benefit of this, not adapting the focus size. We can also maintain the short pulse duration over all rep rates. You can see that if you relax the focusing and the intensity at the crystal, it's giving you a smaller bandwidth slightly. So here in this case at 4 megahertz the pulses are a bit longer, but this is only because it was not optimized for this repetition rate. You can also see the corresponding spectra here on the graph on the right bottom. For 200 kilohertz and 2 megahertz, you almost achieve the same bandwidth as the focus is adapted, so the intensities at the crystals are more or less kept the same. If we don't do this, then the bandwidth is shrinking a little bit at 4 megahertz, but still covering quite a wide range. What we have explored lately is tunability. So as we're using quite short pump pulse duration, spectral filtering can be done in the time domain by just applying a slight chirp of the signal pulses. You can see this here on the left in these sketches. So if we delay the signal in respect to the pump, then we can just generate or amplify different bands of this broadband signal. And on the right top, you can see if we do this with a bit lower dispersion, then we have about 30 to 40 femtosecond bandwidth, and we can tune it over a range from 680 to almost over 850 nanometers. But this is mainly caused by the third order that we used when we chirped this with fused silica material. If you apply a larger chirp, the spectrum gets more narrowband and the tuning range is here extended, and this gives you nice about 100 femtosecond transform limited pulses, tunable over a wide range from sub 700 to 1 micron. What is interesting in our view is that due to the absence of storage time, the speed of the wavelength tuning and switching is only limited by the speed of mechanical movement that you can do. And in order to show that this process can be intrinsically quite fast, we just did a simple switching by rotating material through the beam. And you can see we can switch the OPCPA from 700 to 800 nanometer here on the left top in green or in red on this logarithmic spectrum, and detected then the switching of colors by 2 photodiodes that are placed in the Fourier plane. And here you can see that within less than 2 milliseconds, we switched between these 100 nanometer spectrum. Please note that this transition here is not caused by any real physical effect, but by the passing of the round substrate through the beam, which was definitely not ideal. But intrinsically, the message is this switching can be done very fast with a tuning speed here of, or switching speed here of more than 50 nanometer per millisecond. That's definitely not the end. Okay, then CP stability is quite important for a large range of applications. As I told you, starting from a Tile-Sapphire oscillator, which is CP stable, essentially what you have to do in the parametric process is compensating for drifts or any other variations that you might have, slow variations that you might have in the amplifier system. And if you apply a second feedback loop, which can be easily done by generating some white light, measuring the phase after the setup, and feed it back to the initial loop, you can see that we can achieve quite good CP stability. And this is an ideal source then also for high harmonic generation that has been done here in cooperation with Lund University and a group of Anier. And you can see that with these high rep rate micro 2 level pulses, it's possible to generate quite nice harmonic spectra and see the CP stability here on the right bottom. You can see that at higher energy, you can see a CP effect by changing, in this case, a BK7 glass wedge through the material. And please, for more details, look at the publication here in Europhysics Journal. Okay, so now in the last 5 minutes maybe of my talk, I want to give you a short introduction to the physics of OPCPAs itself. So phase matching geometry is one thing that can actually have quite important effects on your results in OPCPA generation. And so you can see here in this phase matching curve, so on the bottom again is the non-collinear angle alpha, the wavelength on the y-axis. You can see that you have two options for positive and negative angles. One is called tangential phase matching, one is called pointing vector Walkoff geometry. And the main difference between the two is actually the direction of the pointing vector, which in one case points in the direction of the signal, and in the other case, in the tangential phase matching, points more in the direction of the idler. And so this Walkoff effects can have, especially at small focus volume, quite some effects on the outcome of your OPCPA. So what has been done at the group of Uwe Morgner in Hannover by Tino Lang is numerical, called it 2D+1 simulations. So what you more or less do is you try to consider all nonlinear effects here, like second harmonic generation, self-phase modulation, and the spatial temporal domain, and then you go to the spectral domain where you take account for dispersion, diffraction, and walk-off. And with this model, it's quite easy to have propagation through the crystal, with low calculation times, let's say. And I had a nice video which is not playing here. So in principle, what you see on this slide here is the profile on the left from pump, signal, and idler. And while you're propagating through the BBO crystal, and on the right side you see the spectrum here in black. This is the initial seed spectrum, and in pink you can see in the background the OPCPA spectrum that we measured after one stage. And if you run the simulation, so I jump to the end, you can see the pump profiles, signal profiles, and the idler on the left after amplification in this 5 mm crystal in this case. You can see that the simulation yields quite good agreement to the experimental results for this amplifier. So it's quite a good tool for us to understand the process itself and design the amplifier system. One of the nice benefits of this simulation is also that you can identify the various nonlinear products that you can observe in OPCPA. Here on the top, you see a picture actually taken, so where in the middle you can see a round black hole. This is actually where the pump is passing through, and then it's just taken kind of a screen through this amplification, angular dispersion more or less. So alpha is the non-collinear angle here again, and you can see that at 2.5 degrees we have the amplified signal beam here, and which also has some second harmonic to it. Then we see other mixing products that are explained in this paper below. And on the other side, for negative alpha, we can see actually the idler ranging in the IR, and on top, what you see in orange is actually the frequency doubled idler. But there are also additional mixing products that we can observe in the experiment and also in the simulations. And that's gives us a quite good insight into the process. What is more important for us in the end is choosing the right geometries, and this here in this slide I will summarize simulation results, and in pink in the background you can see experimental measurement data for different OPCPA systems. This one is one from Anne Hart and University of Hannover that I showed you for the pulse synthesis. So for low pump energies, as in this case, there was a quite small focus size applied with about 50 micrometers and 5 millimeter long BBO. And you can see that the Poynting vector Volkoff geometry and the tangential phase matching yield quite different results. So the beam profile, as you can see on top, and also group delay is quite modulated in tangential phase matching, because the Volkoff effect generates a permanent conversion or regeneration of the signal, whereas in the Poynting vector Volkoff it seems quite a bit more controlled, and you can more or less better compress this pulse, and the angular chirp is less. So if you use a medium pump energy and geometry, the geometry is still important for good beam quality and pulse compression, but you can already see that the effects of the two geometries are less pronounced, the differences are less pronounced. Still, in this case, we have a slightly better behavior, especially in the angular chirp, if you go to a Poynting vector Volkoff compensation geometry. And then if you scale the pump energy higher, then you can relax the focus size, and also the differences then get less pronounced. And you can see that the spectrum between Poynting vector Volkoff and tangential phase matching are more or less equal. And then the main difference actually is that there's a parasitic phase matching, which is in Poynting vector Volkoff around 870 in the middle of your amplification band. So this is a power loss, and actually tangential phase matching in this case is a preferred option. Okay, so this brings me almost to the end. So you can try to extract some design criteria for a few cycle OPCPA system. So what you would like to have is an intrinsic synchronization between signal and pump pulses for low jitter and noise. Short pump pulses facilitate actually the broadband recompression of the signal, as you have to match the pump pulse duration in the NOPA crystals. You don't want to stretch a broadband signal too much, so recompression becomes really a problem in the end. So for a hands-off system, you need an active delay control for stable long-term operation. You normally want to operate with peak intensities around the 100 gigawatt per centimeter square level, so that you have a high efficiency, but also not too high, and you want to stay below damage thresholds of the crystals. Non-collinear geometry allows you a wide bandwidth, and 2 or more stages give you freedom of tailoring the amplification in the stages and adapting the focus size. Dispersion management, especially for few cycle pulses, is quite an important aspect, and you would like to have that up to high orders. In our concept, we manage with our broadband chirp mirrors, but other groups also implement pulse shapers for this purpose. And in the end, the requirements that you need to have an application, an OPCPA that's well suited for application, is that, of course, you want to operate it below damage threshold to avoid optical damages. You also want to avoid oversaturation and back and forth conversion in the parametric stages, because this will actually affect your beam profile and also compressibility of the pulse. So you want to maintain a good spatial profile without angular chirp, so you have to do some efficiency trade-offs here. And geometry can be quite an important factor depending on the pump energy that is available. So Volkoff and spatial temporal coupling can lead to aberrations and to complicated spectral phase patterns. So temporal background in the pulse and peak power reduction might be an issue in this case. Okay, so I'm now at the end of my talk. I want to thank you for your attention, and also invite you to visit us at the laser show in Munich next week and see our live running OPCPA system at our booth. Okay, thank you very much.
Thank you very much, Thomas. We now have sort of 10 to 15 minutes to answer, hopefully you can answer some questions that have been presented by some of the people that have joined us for the webinar today. I can jump straight in with those if that's okay with you.
Yeah, sure.
Okay. So we've had a question here which actually asked, and obviously for the people that are listening, if you have any questions that spring up, please feel free to ask those questions directly. If we don't get through all of the questions today, then we'll certainly make sure that someone from Laser Quantum is contacting you directly to answer those and get back to you on that. Okay. So one of the questions we've had here is, what is the benefit to start from one broadband oscillator instead of starting from a different laser or using white light generation?
So in the end, in my opinion, the target parameters that you want to reach are quite crucial to answer this question correctly. So if longer passes are okay for you and around 10 femtoseconds, and tunability is one of the main aspects, white light generation is a way to go forward. In our case, we are mostly focusing on even shorter passes, and CP stability is quite an issue. And as you have seen maybe on the overview slide, starting from this broadband cedar without any nonlinear broadening gives us quite low noise and an easy way to stabilize these few cycle passes, to stabilize the cavern envelope phase. So in principle, that is one of the main benefits. And Sapphire technology has evolved quite a lot, also from the commercial side in the last 2 years. So these systems can operate over weeks and quite maintenance-free. So I think in terms of stability, both concepts are quite similar. But I think especially if you want to focus on few cycle and CP, I see quite some benefits in starting off from an ultra broadband feed stemming from a Sapphire, because CP is quite easy to stabilize, and you have a very well controlled phase relation from this oscillator.
Okay, thank you. So one of the other questions we've had here, which seems also pertinent, is what are the power limitations of the technology if there are no thermal constraints within the nonlinear crystal?
Yeah, so in principle, in this quick overview, I cannot address all the details. Of course, there are also some power limitations. So in principle, you have to, I think, in the slide that I presented, you have to, in order to claim that there is no absorption, you have to consider also idler absorption. So if the crystal is actually producing or absorbing some mid-IR generation, mid-IR radiation that is generated in the process, this can lead to heating processes. And also two-photon absorption can be an issue if you use mid-IR crystals like KTA, for example. Also, you have to consider these issues, but it's not a direct heat absorption from the process itself, but from kind of corresponding radiation, more or less. So this can limit your power, but in principle it depends on the crystal and wavelengths, pump wavelengths that you choose. Intrinsically, you can, by keeping the intensity at the crystal within some limits, which you can normally do by adapting focus sizes, you can scale it up quite efficiently, as you have seen, also in terms of energy. And then mostly the pump lasers will determine your limitations. So that was also the reason why I showed you different concepts. So if you go for a thin disk concept, for example, this is quite good in kind of managing nonlinearities, because the crystals are quite thin. There's only pocket cells, more or less, in the regenerative amplifiers. You can produce, as you've seen, 200 millijoule level pump energies. And if you look through the publication, this is not the end. So there are quite dramatic plans in the group of Hans Klaus in Munich to scale this up even more. So they're talking about kilowatt levels. And if you go for fibers, I have forgot to mention this explicitly, but you can also do pulse combining, so several kilowatts of average power have been generated there. This technology is maybe limited a bit earlier if you look at pulse energy. So these are more, in my opinion, more suited for higher repetition rates.
Okay, thank you. I mean, one of the other questions we've had here, so which would follow on from that, is To acquire the least noise on CEP, what pump mechanism do you recommend, fiber or sapphire?
Sorry, can you specify this question more? So it's about CEP noise?
The question we've got here is, to acquire the least noise on CEP, what pump mechanism do you recommend, fiber or sapphire?
So in principle, the intrinsic CEP stability is given by the signal, first of all. So you have to have a quite low noise CEP stabilization, and there I would definitely prefer sapphire laser. There is some work that has been done by several groups about coupling from pump noise in the parametric process to CEP fluctuations. So you have to make sure that you have a quite low noise pump laser, also that you don't transfer additional noise into the process by a nonlinear coupling. And in my opinion, fiber laser technology, especially if you operate them in saturation, are quite good candidates to also have low pump noise. So that would be my preferred way to move forward. If you go to fiber-based, completely fiber-based systems, mostly people are going to different frequency generation. As you have the carrier envelope phase as in the signal and also in the pump more or less, then it can cancel out in the idler. So it's passively CEP stabilized, and also results there are normally on the same level. So, but it's a different method of generating the CEP stability, and also what is our main aspect here is also different wavelength range. So you're normally in the mid IR or in the near IR around 1.5 microns or so.
Okay.
I'm not quite sure if I understood the question completely, but this is what I...
Okay, well, what we'll do, obviously, at the end of the webinar, all the questions will be passed across, and you can follow up with everybody directly. We do have another question here, which actually says, are 515 nanometers and 532 nanometers about as good as a pump?
I would just say that, as you have seen maybe quickly on the phase matching condition, especially we are mostly working with BBO, it's quite relaxed where you pump it. You can also pump it with 600, then you just shift the whole phase matching bandwidth more or less. And in this case, what is the ideal pump wavelength? It would mainly depend on the pump technology that you're using. So if you're using 532, that's normally vanadate. That normally gives you different pump technology. So we have done work with a solid state terbium-based, vanadate-based amplifiers. There often the bandwidth is not so high, so you have several picoseconds of pump pulse duration, and then you have more kind of issues with stretching and compression. The parametric process itself works the same. So we got similar amplification. The main difference is the pump pulse duration in the end. So I think this question is really relating to what is your preferred amplification scheme.
Okay. I think we've got time for maybe one or two more questions here, if that's okay. We have one here. How long are the pulses overlapped within the parametric process, and how are the pulse durations set?
So in principle, in our setup, we have quite short pump pulses. So as I mentioned, sub 300 femtoseconds. So the signal actually doesn't really have to be broadened so much because it's broadened by itself. As a consequence, you have to use quite short crystals so that you stay within the pump overlap. You will always have some evolution. You also have some group velocity mismatch in the crystal. So if you're working with such short pump pulses, you should use rather short crystals. Typically 2 to 3 millimeters maximum, even shorter preferentially, and to keep them overlapped. You can also have a different concept where they actually, as in this tuning scheme, amplifying different frequency bands more or less, but we prefer for the normal OPCPA system to have a preamplifier more or less where we apply lower pump power, and the main amplifier as NOPA stages which cover the full bandwidth, so we have to maintain the pulse duration in the crystal more or less under the pump pulse duration. So it's about dispersion management of the signal in the end and having short crystals.
Okay, thank you very, very much. I think that is just about all the time we've actually got available to answer any further questions with regards to the webinar today. What we will, of course, do is get back to everybody on direct email, so we can answer everybody's questions. And also, you can contact or meet up with Laser Quantum at the Laser Exhibition on booth Hall B3, booth 314. Okay. Would you like to add anything further, Thomas, before we wrap everything up?
No, just as I said, first of all, thanks for your attention to all the audience, and then I hope to see you in Munich. I will be at the booth mostly, so I would look forward to have also our discussion maybe there continuing.
Well, thank you, everybody, and have a good day and the rest of the afternoon. Thank you very much.